Right. Another leak code stream today. Yeah, so actually coincidentally, like this is the third stream or stream number 3, and we're gonna be working on trees today, which is quite funny. Uh yeah, so I'm just gonna drink some water. I've never like really done any trees questions for lead code, so this could be like very difficult. I'm hoping that it's a lot easier than I think it is, but we'll see what happens. But yeah, man, pretty good day today. It's raining currently, so it's a little dark today, but yeah. All right. All right. Cool, 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 cool. All right. I guess let's just get right into it. Inverting a binary tree. Yeah, so I think for today I'm gonna do this, I think 5 questions. So maybe invert binary tree, maximum depth of binary tree, diameter of binary tree, and balanced binary tree. I think the balancing one's gonna be quite difficult because I've never really properly digested the balancing algorithms. So yeah, this could be a bit difficult, but that's fine. It's what we're here to do. Alright, question number 1. Inverting a binary tree. So, given the root of a binary tree, invert the tree and return its root. So we have, okay. So essentially, what I can see here is that for every node, essentially flip the left and right nodes. I think that's what's happening. This should be fairly simple, I think. I think I understand it. So let's say we're starting at our root node of 4 and 2 and 7. So all we need to do is flip 7 and 2. Then we go to 2 and then, or we basically go down all the way to 2, flip that with 3 and 1. And then go to 7, flip that 9, and then 6, and then flip that 7 to 2. So I think we'll do like a bottom-up approach, I think. Okay. I think that makes sense. So likewise for here, if we have these two, so then just flip that. I guess we could start from the root and then flip the left and right, move down to left. I think that would work. Let's see. Okay. Immediately, the way I'm thinking is to use a queue, so like pending nodes that we need to flip. So let's just say nodes is just a list. So then we say, and we'll say nodes starts with the root. And then say while there's something in nodes, so while length of nodes is greater than 0, what we can say is that, so while the length of nodes is greater than 0, what we want to do is we add the left and right, but at the same time for the current node we flip the left and right nodes. So we say that current is equal to nodes at 0, I think, or we pop at 0, I think. Nodes pop 0, so we get like, we remove it straight away and remove the first one, I think. So then once we do that, all we need to do is append left and right to the nodes array. So if current dot left, I think like this, I reckon. If current dot left, then all we need to do is append that to our nodes. Append, if I can spell it correctly, append current dot left, and then we do the same thing for the right one. But I suppose if we are flipping it, then it doesn't matter. So we'll just do that then. Actually, yeah, actually, never mind. It doesn't matter. So we can just do temp is equal to current dot left, and then we'll say current dot left is equal to current dot right. This is meant to be right, and then we'll say current dot right is equal to temp. Oh wait, yeah, I actually meant to do the left bit here. My bad. Yeah. I think that makes sense. So let's just kind of reiterate here. So basically we have a list of nodes, of like pending nodes that we haven't flipped. So we start at the root, and then while the length of nodes is greater than 0, all we do is we basically remove the node at position 0, set the temporary to be the current at the left, change the left to be the one at the right, and set the right to be the one at the left previously. So that works, I think. Yeah. Okay, yep. So then but we also have to append the nodes itself. So if current dot left, I keep adding brackets for some reason. I think you're not supposed to. So if there's a left node for the current node, then we basically say we just append that. And I think that should work. And we also do the same for right, because it could be the case that like it has a left node but no right node. So we want to make sure that we take that case into account. And if we have a right node, we just append the right node. So yeah, I think that should be okay. Let's see. Alright, so then all we need to do is just return the root. And I think that should be okay. Let's just see what happens. Please, if I get this first try, that would be huge. Current is not defined. Yes, thank you. Let's see. Alright. Come on. Non-type object has no attribute left. Okay. Okay, wait. Alright. Non-type object has no attribute left. So that's interesting. Okay, wait. Nodes dot pop 0. Does pop actually return it? Maybe it doesn't actually return anything, you know? Pop first element, maybe. Okay. Okay, if we have this using the list. Okay, so pop. The remove is one of the most commonly used. Removal by items. Okay, so if you remove 22, but that's not what we want to do. You want to remove by index. So you can't use remove, I don't think. We could pop, I think. Okay, yeah. Wait. Yeah, I think the actual pop method doesn't return it. So, okay. So we'll just say current equals to nodes at 0. And then we'll just pop at 0 there. I think so. I honestly thought that like if you pop it, it straight away returns what you've like removed. But hey, I guess not, but that's fine. Maybe this works now, I think. Maybe no, we still have that same issue. So maybe it did work just now. It's just that maybe it's not popping the right thing, maybe. Let's see. Let's just print it, see what happens. I'm hoping to see like some values for it, but non-type has no. Okay, that's this is really odd. Because if it's current dot left, this should have worked. Why is it not working? Let's see. So it did print it. But it's not. this? Okay, wait. It should have worked. I don't understand why it's not doing it. Current dot left. Non-type object has no attribute left. Bro, anyone got any ideas? I'm so confused. I thought this... Okay, because clearly current has all of these values. So it should have the attribute left. Right? I think. And then it also has the attribute right. But it's not showing up for some reason. That's really odd. Okay. If current dot left. Did I spell it wrong? I didn't. So... okay, wait. Okay, attribute error, non-type object has no attribute left. If current dot left. This, okay. Interesting. It should have done it there, but for some reason it's not working. Bro, what is this? Okay, this is a really bad start for the very first question. Alright. Because I think this should have worked logically, but, you know, obviously not, maybe. Alright. Notes pop 0, print current. Current did show up here. So I'm not sure why it has no attribute left. Am I supposed to do it like this, maybe? Like, left. Surely not, right? It's not scriptable. Okay, that's good to know. This is really weird. Okay. Come on. Non-type object has no attribute left. Okay. That's brilliant. Why though? Node stop, parent current left. Current, print current. Print current dot left. Let's see it. Maybe that could help. I don't know. Oh, okay, I got it. So basically it could have went down all the way to the none type. So what we needed to do is do current and that. Yep. Or, yeah. Basically we can just do if current. And then we'll just put all of these in its own loop. And that should work. Because what was happening was that it was fine for the first few ones, but then once you reach these leaf nodes and they have like a left of none type, then that's when it became an issue. So yeah, I think so anyway, but yeah. All right, hopefully that works now. Maybe. Nope. Okay. Maybe we can just put all of this in here. Let's go. Alright. Please. Hey, not bad. Alright. Yeah. I guess that's it, right? Yeah. So let's just try to analyze this quickly, see what's happening, see what the runtime is. So, you know, considering we're visiting every node, the runtime is definitely a big O of n, where n is the number of nodes. So because we're essentially adding each node to the nodes array, and because we're also appending that, then I believe our memory is also big O of n. So let's see here. So basically, while we're doing that, we're popping that, so we're getting the first element, which is pretty okay. And then, yeah, basically doing a conditional, which is a constant time, I believe. So yeah, big O of n. So I think that should be one of the more optimal results. I'm not sure. Let me just compare to see how other people have done it. Let's see. So if not root, so if the root is empty, then return none. Then you get your left, you get your right. So I think this person did what do you call it? This person did recursion. That's pretty smart, actually. I didn't think of that. So if not root, return none. That's quite cool. Alright. So then you basically swap out left and right. And then you keep calling that and you just return the root. That's really interesting. So let's try make our current solution more optimal. Okay. I guess we can start off with a base case, right? So if maybe if current, if not root, I guess, yeah. So basically if the root is none type, then we just basically return root, I think. It could be empty, but I mean, that's fine, I think. Maybe. This should still work, I think. Is there a way to make this better? Because, I mean, like, we don't really have... I think the sort of logic that I have is pretty much the same. Unless we can just swap it out regardless. Like that. So we don't actually need those conditions to check if they're valid, I think. Because this already kind of does that for us. But my worry is that if it appends non-types into... Yeah, that could be an issue. And what I was basically thinking is that if, you know, just like append it regardless of it, but I think that wouldn't work because it'll go into an infinite loop, I think. Because, oh, never mind. Hello, Arnav. Welcome back to the stream. Good to have you on here. The goal for this stream is to just basically do some tree questions, since it is also the third stream. Yeah, alright. I think this solution looks a lot better, maybe. I mean, I don't know, but we'll see what happens. And yeah, it's slightly better, but this is my solution a long time ago. So this solution also did use recursion. I guess recursion is a good way to go here, but I kind of just wanted to do it with the, what you call it, with just a normal loop. I think most solutions in this sort of category did normal loops. Actually, no, most of them did recursion. This one didn't, so that's good. Is recursion generally faster? I don't know, but judging by this, probably. Yeah, I'll just write a recursive solution for now. So basically, for any recursion, we always need our base case, right? So basically, if the root is an empty, we just return none. Otherwise, what we can do is we basically create a temporary node that's equal to root.left and say that root.left is equal to root.right. What were your grades in high school? High school, so that's like, I guess like I got 3 A pluses. I generally like when it came to the final exam. So I did like A levels as well as IGCSEs, and for both of them I was able to get like straight A pluses. But when it came to like I only crushed it for the final exams. But if it came to like midterms, that sort of thing, I usually get like 80-ish. I don't think I had a GPA. I guess like the closest thing to I had a GPA was always like 3.5 or something like that. So I guess decent, I don't know. But honestly, I'm like, although I know like math and stuff, I'm like pretty dumb when it comes to computer science. Like there's so many stuff that I still don't know. I guess my goal for computer science is to kind of like pick up more algorithm stuff. That's essentially what I want. But yeah, man. High school. Yeah. My grades were alright in high school, but I, didn't really do much coding, so it was still pretty much an L. Alright, so then we just swap root.right is equal to temp. And then we just run self.invert tree for both sides. Root.right. Root.left. And then we'll just return the root. That should be okay. Let's see it. Alright, nice. You see the runtime here is 75. I got like 60 previously. So it's interesting to see like for lower cases, they're the same, but for larger cases, it's very different. Let's see it. Yeah. Pretty much. Yeah. That's what I also find interesting is that my solution is pretty much the same as like this, for example. So it's interesting to see that it is different, even though the solution is pretty much exactly the same. So, yeah. Oh well. Let's move on. Done that. Let's go. Alright. So, maximum depth of binary tree. Given the root, return its maximum depth. A binary tree maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So I'm assuming this one's 3. Yep. So we have left and right. And then we just keep going. That's interesting. Okay. Alright. So this is considered 1 depth. Then this is 2. And then this is 3. Okay. Alright. That makes sense, I guess. Oh, this is interesting, you know? Okay. So I don't think we can use recursion for this one because we don't really take that into the function. So we're just gonna basically loop. We could do a bottom-up approach. I think that would be good, but how would we do that? Okay. I guess we can say that. So if we have a null root, we can just return 0. Okay, so as long as we have 1 node, then our max depth is 1. So what we can do is we just say Hmm. I guess we'll just create another list of nodes. So we have another list of nodes starting with our root. So then while length of nodes is greater than 0. This is, I think, what you call tree traversal, I think. I think it's depth first search, but I think, how do you do it? So we have our node, our root node. That's our core. That's how we're gonna find this depth. So then, okay. So then if, so if our current node, so we'll say current is the palm of it. Current is equal to nodes.pop at 0. I think I can just do pop without 0, but I'm not gonna find out. So if current dot left or current dot right. Okay, so basically if it has a left or right node, what we need to do is, I guess, add 1 maybe. Max depth plus equal 1 maybe. I think so. And then we just add the left and right nodes to the nodes list. I think. Oh, I'm not sure actually, because that wouldn't work. Because let's say if we have like, because let's say if this one had another one, then that would be 1 plus 1 plus another 1, so that would be 3, which isn't the correct answer, obviously. This is interesting, okay. Alright. Okay, yeah, this is actually kind of hard, okay? Because if we start at here, I guess what we could do is just because I think the current one that I'm doing, if I'm doing left and right, that's breadth first search, which isn't what we want. So I think so anyway. Bro, I don't know. Yeah. Current dot left or current dot right. So if we have, surely there's like a mathematical relation to like this list, you know, to like the depth, the maximum depth. Oh, yeah, but that's probably not like, yeah, actually. Okay. Yeah, this is quite interesting. Because if we don't have a root, then we just return 0. Then we say our max depth is equal to 1. But then how do you actually traverse this binary tree? We could go left and then go left. Okay. I think we should use a stack for this. I think. So it's like, no, actually I don't know. Because we have 3, 9, 20, right? So then we could just append, so 3 is at our root node, and then we have 9 and then 20, so then when we go to 9 we add that to 3. Wait, what? Okay, so while length of nodes is greater than 0, if we say that we have the current one, what's a better way to do this? Because we can't just... Because my initial idea was that when we visit here, we append left and then right, and then we go to the left, and then see if there's a depth for that. But then that wouldn't work, because if you keep appending one for each like depth you go, then that's not gonna work, I don't think. So yeah. There's definitely like a mathematical relation to this though. But yeah. But how do we visit every single node? Okay, so let's say you're at this node right here, yeah. Let's say if we're at node 3, then we go left. Okay, right. So instead of getting the first one, because if we get the first one, that's a Q. So we just pop the last one. Okay. Yeah, wait. Okay. Because what I'm thinking is that we say 3 and then this one. So then if current dot left, then we basically add left to the end. So we'll just append that to nodes. Append current dot left. Same thing for right. I think so anyway. Yeah. Okay. And current dot right. Current dot right. So yeah, so you append left and then you append right, and then what do you do? I feel like you should add 1, but I don't think that's how it works, because that would basically be called every time you have a new node that's like added there. Oh, okay, this is kind of tricky, you know? Okay, so append left and then append right. Then oh, okay, yeah. I'm stuck. I have no clue what's even going on. So I'm just gonna watch this solution, because I have no clue, dude. Alright. Let's see it. So recursive depth first search. 1 plus the max. Okay. 1 plus the maximum of depth first search left. So I guess you define like your own depth first search algorithm or function rather. This one you could have a queue. Yeah. There's like a couple solutions to this. So it's kind of interesting to see. Yeah. So this one had a queue instead. So 3, 9, 20, 1, 2. Okay. Level equals 1. Q is DQ, while Q for iron range and length of Q. Length of Q. Okay. Top left. If node dot left, then Q dot pen node left. If node dot right, Q dot pen node right. Level plus equal 1. I guess that kind of makes sense. The idea here, I guess, it's you have a queue of root. Yeah. Yeah, that's quite interesting. I'm still like confused with this thing, but I suppose like the idea here is that you basically have to recursively go down like some way. I feel like I was kind of close with this, but I have no clue how to actually properly implement this. So, yeah. Because, yeah. I guess, like, if we look back here, right, what he's doing is that we loop through each, like, queue, I suppose. And then you pop the left side. So you get, like, the leftmost, so index 0, I guess, maybe? I don't know. But yeah. And then if that has a left or a right, then you keep appending that. Level plus equal 1. I don't get why he's doing it outside of this for loop and not in it though. I guess it makes sense maybe, but I also feel like this would be decently slow as well, but let's just hear this solution real quick. Because I think, like, I understand this recursive depth first search one. The idea is that you would just want to get like the current node plus the maximum of the left or right one. That one I understand, but this breadth first search one is quite interesting. So let's listen to that one.
The time complexity is still going to be the same. The memory complexity is still going to be the same. But let's still do this for learning purposes. So breadth first search on a tree is basically level order traversal. We're traversing each level by level until we get to the end or the last level, and then we can't continue anymore. So you can kind of see how breadth first search is a pretty intuitive way to find the max depth, right?
Okay.
We're basically counting the number of levels we have. So here we see, okay, we have 1 level.
Yeah, that was my initial idea as well when I wanted to code my solution, but I'm like super dumb, so I can't figure it out. But I would like to say that I was close at least. Nah, I'm just.
Now the only problem is how are we actually going to code this up? Now typically BFS involves a queue or a deck, a DQ or however you call it. And so the way it's going to work is the queue is initially just
first in, first out
root value. So I'm going to kind of represent this array as the queue. So initially we're just going to put the root in the queue, right? So now we're going to say, okay, what's the length of our queue? These are the elements currently in our queue, and these are all at level 1. So now we're going to go through every node in our queue. We only have 1, and we're going to take 3. Now we're going
to... Okay, I got it. All right. So my issue was that I didn't know how to differentiate if a certain, like, let's say if we appended left and right, then how do we know that they're the same level? But now I get it. Now I get it. So all we need to do is basically every time we have like a new node, we append the left and right ones, and then we say that that's a new level, exhaust all of the, make sure that left and right is already finished, and then like keep adding more to that. I think, yeah, so what he's basically saying is that you have 3, right? From there, you iterate that through once, and then that's at level 1. And then you, for that specific one, you add 9 and you add 20. And then that is a level 2 now because you've done that. So that would have been added into the list. And then once you loop again, you loop through all of the child nodes for 9 and the child nodes for 20. You append that, and then you keep going, essentially. I think so. I don't know if that made any sense, but, you know, we're just gonna go for it. So we have our nodes, right? We have our nodes, we have our nodes array right here. All right. Beautiful, beautiful array. So we basically get the current one, pop at 0, I guess, maybe. Yeah, no, wait, no. Okay, yeah. For I in length, for I in range, jeez. Rage, yes, I can definitely spell. So basically, for every single node in this, basically, we want to get the current one at I think so, wait. Yes, yeah. And then we basically keep adding that to nodes. Yeah. Yes, wait, yeah. And then we basically say, max def plus equal 1. Then we just need to return max def. Yes, okay, cool, this looks good. So basically, if we have like the root node here, all we need to do is just loop through that, and then we basically pop it from there, and then add that. But all right, let's just say new nodes. It's just an empty array for each visit, I think, because I'm scared if like this basically affects this loop. So then they'll be, actually, yeah, let's just try without it. Let's see what happens, because I'm hoping that this sort of fixes it, because if we keep appending, I don't want it to be like an infinite loop. But I think that shouldn't be the case, but we'll see. Pop index out of range. Okay, yeah. So that's probably because we're appending. So I guess maybe new nodes is empty. And then new nodes, append that. So we do it every time we're about to start that. And then we say nodes equal new nodes. So let's just reiterate what we're doing here. So first we have a list of nodes, right? At first it's just going to be our root node. And then we define an empty list of new nodes. And then for I in range length of nodes, for this, basically this first one, we basically say that the current one is at the nodes.pop at I, which will be like, oh wait, actually we can just do 0 here. Oh, yeah, I think that was the issue. So we could have just popped at 0 and continued. Or actually maybe we should just access it normally like that. So we basically loop through all of our current nodes. So maybe we don't need this one in this. So, yep. Okay, let's go through this thing one more time. So we have nodes, which is a list of roots or a list of nodes. And then we basically loop through this nodes list. We say that, okay, the current one is, we basically loop through each of the nodes and then say that if it has a left, then we append that one to the nodes list and append the right one as well. But hopefully, I'm not sure if this is actually the case, but hopefully when you append like that, it doesn't actually affect this loop, because that would be an issue. Let's just run it. If this goes on forever, then we know what the case is. Does seem like it's taking some time, so yeah. So I think we need to define a new nodes array. So let's just say new nodes is equal to empty. Then we just append new nodes here. This is like super inefficient memory, but you know, I'll just take it, bro. And then we'll say nodes is equal to new nodes. Okay. Yeah, I think that makes sense. Let's see what happens. Output is 4, expected 3. Let's just say max depth is 0 then. Alright, let's run that. I think this should work. Yeah, okay, cool. So the issue why is because like it would automatically it automatically adds one even though like our current node, because we're looping through this root, right? So we didn't need to take that into account. Maybe that's okay. It's definitely not like the most efficient, I reckon. Actually though, that's not bad, you know. 83.91%. Alright. I mean, I can't be too proud because I literally had to refer to Mr. Need Code, but that's fine, you know. Let's see what the top people did. So here, I think this is basically doing recursion. Not root return depth, then return max of this. Yeah, that makes sense. Basically, the idea is that you define a depth first search and you define your base case, and essentially depth first search just returns the maximum depth for the left node as well as the right node, maximum between the two. Yeah, that makes sense. It's quite interesting. And for this max depth, you just return either this or 0. That's quite an interesting solution, actually. Yeah, I think most people also did it that way, I think, maybe. I mean, this guy did define his own helper function. This guy didn't. So if root is none, return 0. Left height is equal self.max. How did you learn algorithms? Well, welcome to the chat. I guess mainly it's definitely through university. Although I didn't pay much attention, I'm not gonna lie, for my course. But yeah, I think university played a very small part for understanding data structures. But for algorithms, it's definitely just been practicing lead code, I can't lie. Like just watching a lot of neat code tutorials, because I think it's just interesting in general. But yeah, so that's why I suck at it, because I haven't really done that much. I think, but I mean, like in uni, for example, they don't really, at least haven't really taught certain algorithms that is needed for it. So, but they did teach like depth first search and breadth first search. So I definitely should have paid attention for that. But I understand the basic concepts of each, but I don't really know how to implement certain algorithms. So yeah, that's why I'm practicing each week, just trying to see how it all works. So yeah, that's quite interesting. Let's go back to this solution actually. So you see that it's self.max depth, it's that yeah, recursion is definitely a lot interesting, because it's like it could go on infinitely if you don't know like what you're doing. So I always find that quite interesting. Self.max depth, root.left, so you just essentially return the max of the left, right, plus 1. I guess that makes sense. So like in the base case, if you just have one node, this would just return 1. So yeah, that is quite interesting actually. Yeah, but I don't like how this maximum function is doing a lot of the heavy lifting, which is why I didn't really want to write that solution. Whereas here, oh, well, not this one, but a lot of them actually do that. But when you do like this like sort of iterative type of loop, you don't utilize the maximum thing, so there's no like, it doesn't really have that heavy lifting for you. But I guess it kind of makes sense, but you know. Alright, I'd say that's done. I'll try write the, what do you call it? I'm gonna write the recursive solution now. So we define our base case right there, and I guess we just return 1 plus the max of self dot max depth of root dot left, and same thing for the right side. So yeah, I think so anyway, but if I remember it correctly. But I mean, the idea is that you just kind of 1 plus and then do that same thing for left and right. Then yeah, that should work. I don't know if I want to submit the solution though. You know what, screw it. Just why not, right? It's definitely not going to be as fast as some of it, but yeah. Alright, cool. So maximum depth of binary tree is done. Diameter. Next one is diameter. I'm pretty sure this is going to be a breadth first search type of thing, but we'll see. So I guess this one's 2. Oh, 3 actually, never mind. So given the root of a binary tree, return the length of the diameter of the tree. I think, is diameter defined like 1, 2, 3? It probably is, right? The diameter is the length of the longest path between any 2 nodes in the tree. This path may or may not pass through the root. The length of a path between 2 nodes is represented by the number of edges between them. Oh, okay, so 1, 2, 3. Okay, that makes sense. Ooh, okay, this is interesting. Okay. This is gonna be another hard one, bro. Ugh. Okay. Now, let's think how this would actually work. So let's say we start at the root, have our left, and we have our right. Let's just make this a bit bigger. Yeah. So we have our left and we have our right. We can definitely say that that is just a 1 and a 1. Bro. Okay. Then if we continue to, we go through the left, we see that we have another left and another right. And we have a 3 which doesn't have anything, so that's just 0. Okay. I guess we can kind of think of this from like a bottom up approach, I think. So let's say you have a 4 here. Alright. The maximum what do you call it? The maximum width of this is just gonna be 0 if you're just at 4. Then you go up 1, the maximum would be 2. Because you compute. Yeah. Or you could say it's 1. Maybe. Oh, I don't know actually. Yeah. Yeah, I think so. So you could say if you're starting from 4 that is no wait, no. Yeah, but I think definitely going like bottom up is the way to go here. So if you start from 4, that's 0, and then you say 2, then that's gonna be 1. Or no, we'll just say this is 1, this is 1. Then at 2 is gonna be 1 plus 1, which is 2. And then because that's 2, you go up 1, that's 3. No, that's definitely not how you do it. Okay. I don't know actually. This is okay. Yeah, trees is definitely not my strong suit here. Clearly, right? Okay. We have 4, 2, 5. So we start at the yeah. That's if we start at the root node, is that possible? Because we can definitely see that this is a 1. Because it could be 1, 2, 3 like that, right? I think that is the diameter anyway. Breath first search. I think this is it, but okay. Yeah, I think I was on the right track when I was saying bottom up. So basically, if we start at 4 because it has no child nodes, then this diameter is 0. But then this one has its diameter of 0. So that's also that. But then this one, because it has left and right, so then that diameter is 2. So then it'll be 2 plus diameter of this, which is 0, diameter of this, which is 0. So therefore for this tree it is a 2. And then yeah. Yes. Okay. Wait, is it a 2? Or I thought it's a 1, no? Wait. Given the root, return the length of the diameter. Is the length of the possible path between any 2 nodes in a tree. So 1, 2. Yeah, so that means this is 2. But if you're starting from here, it's not 2, right? The maximum depth of like... Yeah, let's say this tree is not here, then the maximum is just 2, right? That is interesting. Because if we just have this 2 node, the maximum diameter is 2. But if we include the 1, then it's not 2 anymore. I mean, it's not 3, it's 2. So you can't just say it's this diameter plus 1. So how would we go about this actually? Okay. This is interesting. Okay, so we... Okay. 4, 2, 5, 1, 3. So I guess we can't do a bottom-up approach. Could we? I don't know. Let's say we're starting at the root. Right, so we have our left and we have our right. So... But do we want to start from the root? Because it says it doesn't need to necessarily pass through the root. Because if we had 1, 2, then that's just 1, right? It's just the number, the maximum number of connected edges. Okay. So if we had 2, 4, and then a 5 here. Maximum from here to here, that's... Maximum from here to here is 2. But maximum from here, including this, the diameter is only 2. Bruh, okay. 4, 2, 1 tree or 5, 2, 1 tree. Oh wait, actually, that is correct, right? No wait. Because if you have one in here, then the maximum is only gonna be 2, not 3. This is, yeah, this is quite funny actually. I feel like bottom up is definitely the way to go, but I feel like I'm not thinking about this in the right, like, in the right direction. So we have 4, 5, 2, 1 tree. The maximum here is just 0, right? And here is also 0. But then we go to 2, then that is a 2, because we have one connected here and then another one connected there. Then if we go up one more, the maximum one here is not gonna be 1 plus 2, it's just gonna be 2. Okay. I don't know if that like means anything really. Alright. Yeah, I think I'm just gonna watch. I don't know. Because I want to figure this one out on my own. Imagine 4, 2, 1, 5 tree, right? So, how do we go from there? Okay. Tree is the length of the path. So if we start from 4. So you don't really want to start from the root, right? I feel like that wouldn't be the way we want to go. But I mean, to be fair, like, how do you, if let's say you did start from 4, how would you go up? Because you don't have that value. No, wait, but I guess you could just, never mind. Forget what I said. You could just put in like a queue or a stack or something. I think a stack, definitely, if we want to do a bottom-up approach. So we'll just say a stack. And then, yeah, we'll put a root at the entrance. So, okay, so while we have it stacked, let's just say stack dot diameter of binary tree. Okay. Stack that append. So we have this thing here. We just need to append this and this. Do we? If we're at 1, do we append 2 and 3? I reckon probably. Like, we append 3 and then 2. And then start with the topmost. Yeah, I'm not gonna be able to figure this out, so I honestly need to watch the solution for this, which sucks because it is an easy question, but you know, it is how it is. Alright.
And consider it as, let's say, the topmost node in that diameter. So let's find what's the max diameter from here, from this node 1. Well, we want to go as far down right as we possibly can.
Yep.
We want to find the lowest one node, and we can either go down 3 or 4, right? So basically now what we're doing is recursively finding the diameter from this spot, right? So clearly we can see a
So I guess basically what he's trying to say is that from your root, you basically want the max of the left plus the max of the right. Right? Okay. Let's just go off from that hint. So we don't need a stack, so we'll do this with recursion. So we define a base case. So basically, if the root is none, we just return 0. And then we basically want to return the maximum self dot diameter of binary tree with the root dot left. Let's just zoom out a bit. I can't see anything. Okay, that makes sense. Plus the max of self dot diameter of binary tree root dot right. And we'll say 1 plus maybe, because that's kind of like our current node, I think. So if it's like, if you have like the maximum here is, let's say 0, and the maximum here is 1 or 2, then that would be 0 plus 1 plus 0, which is 3, which is the answer. No, that's definitely not what he meant. I reckon this would work for some cases, I think. Nope, never mind. Alright, because we need to have actual comparisons. Okay, yeah, maybe I stopped the hint a bit too early, so let's continue with this explanation.
Repeated work that we can possibly cut down on. But let's continue the example from here. What's the biggest diameter we could find? Well, we obviously see that both of these paths will lead down to the same level, right? The
Yep.
lowest node could be on this side or on this side, so it doesn't really matter. But what is the length of it? Well, from here, the length is 2, right? And to go from this 1 down to this 2 is also another 1. So in total, this entire side is length 3, right? So we take 3 plus 0 and find that the biggest diameter we could find running through this 1, through this root node, is 3, right? But is that the biggest possible diameter we could find? It's actually not.
Okay.
Right? Let's take this 2, for instance, right? We want to find the lowest node on the right side, right? Clearly, we go down to this 4, then we go down to this 6. So the lowest node is 2 edges long. What about the left side? The exact same thing, right? The 5 is 2 edges away. This is 1 edge, this is another edge. So now we can take 2 plus 2 and find that the diameter running through this node is actually 4. That's bigger than what was running through the root, which was 3, right? So eliminate the repeated work. What we started was top down. We started
Bottom up.
Every find the max running through 3. So clearly we're just visiting every node once so far, right? So what are we going to do? In reality, we don't just want the diameter through this, right? We also want the height of the tree starting at 5, and we can tell that that as well is 0, right? And this part might be a little confusing. It'll make more sense in the code, but basically for each of the nodes in here, we want the diameter and we want the height of the tree. So the diameter through here is 0 and the height is also 0. So then we want to find the diameter and the height for 3, right?
That's interesting. I didn't even think about using the height, so
height of the tree starting from 3. Well, we want to look at its left subtree and its right subtree, right? Find the height of the max of these, right? So basically the max height from left and right, the max height from these, right? And add 0, right? And this just helps the math to work out. So I'm going to leave a -1 here saying that the height of this tree happens to be -1. So then what's the height from 3? Well, the max of left and right is going to be 0, right? So 1 plus 0 means 1, right? So we can put a 1 here for the height of the 3. Well, what's the diameter of the tree? We can find the diameter
this 2.
taking the height
No, it's
of the
1.
left tree So left plus the height of the right tree, which in this case is -1, right? So plus right, and then plus 1 and plus 1. So in reality, plus 2, because for each of these trees we see there's an edge going to it, right? So this edge, right? And what that's going to do is -1 plus 1, that's going to cancel out, right? This is going to be 0, meaning the height from this part is 0. That makes sense. That kind of shows why we're putting a -1 here for the math to work out. What about the left tree? Well, that's going to evaluate to 1, right? Because
Yep, that makes sense.
this is 0. We're adding a 1 here for this edge.
For the edge, yeah. That was interesting though. I didn't think of that way.
Evaluate to is going to be 1 plus -1 plus 2. That's going to end up being 1. It's going to be 0 plus -1 plus 2. That's going to evaluate to being positive 1, right? And that makes sense because just looking at this, the diameter is going to be 1, right? Because there's one edge going to its left node, the right tree is empty, the overall diameter running through this is going to be 1, so we're just going to put a 1 over here. And in reality, this is actually pretty simple. Maybe some of the math is making it more complicated than it needs to be. You'll see that the code is actually pretty simple. But the key here is that we're going bottom up. We're finding the diameter from the bottom nodes and then working our way up to the root. That's what's allowing us to cut out some of the repeated work. So you can see that these diameters and heights are actually going to apply to these nodes as well, right? This node is going to have a diameter and height of 0, 0. This node is also going to have a diameter and height of 1, 1. But what about this?
The diameter is the left plus right plus 2. So it's not like the height, I think, is what he meant. So that's 0 plus -1 plus 2. That's quite interesting how he says like that this height is -1. That's quite funny, I think, because I don't really get that bit. And then let's say you repeat this one. It's just gonna be the left height, which is 1, plus the right, which is also 1, plus 2, which is 4. So 1, 2, 3, 4. That's interesting. So he's plussing 2 because there's left and right, you add 2. That makes sense. And the height is to I think it's just to help for some of the math. So let's say if you have like 1 here, there's 2, but your left height is 1. No wait, this left height is 2. Yeah. Is it? Yeah. No wait. Yeah, it's 2. So that's 0, 1, 2, and then that's gonna be 2 plus 0 plus 2 is equal to 1, or is it supposed to, I think it's -1. Never mind. So any non-type that has height -1. I think so anyway.
The diameter and the height of that node. Oh, and by the way, before we actually do that, remember our max diameter, which we're looking for, is now going to be 1 from over here, right? So we can actually update this and set it to 1 now. So to compute the diameter and height from here, actually all we need to do is take a look at our equations again, right?
So the height is 1 plus max of left and right, so that should be 2, because like the left is 1, the right is height, so then that's gonna be 2. Diameter is just gonna be height 1 plus 1 plus 2, so that's gonna be 4. Yep. Plus 2, so then that's 4.
That's 2. This is also 2. We add those to turning because when you go
Okay.
plus 1, and the height of the left subtree, right? The left subtree is 2. The right subtree is
-1.
And we also have our constant. Remember, we're adding a 2.
So then that's gonna be 3.
Is empty. It's 0, right? So the diameter through there is 0. But take a look at the left, right? This is one edge. This is one edge, and this is another edge, right? So that's a total path of 3, which means the diameter of this.
Well, yeah. So that's quite interesting, I think. Definitely not like what I would have thought of like straight away. Yeah. result is 0. So then you just basically define depth first search. If not root, return -1. Left, you just do the depth first search for the left. Res at 0 is equal to maximum of res 0. 2 plus, yeah. Interesting.
Things for you. So what we want to do now is actually call this function, passing in the root, and then we can just return our result. So you can see that this is pretty efficient because this is a linear.
Then you want to take the max. Okay. That's quite interesting. I don't necessarily know if I properly understand it. I'll code a solution for now, I think, but yeah. So we basically say result is a list, and we're gonna say 0 first, and then we'll just return the maximum of res. I think that's what he did. No, he returned res 0. That's really odd. Okay. Yeah, I don't understand why he didn't just say res is equal to. Okay. Yeah, alright. So then, what do we need to do? Let's just put this back on. Okay. So then we define a depth first search. Depth first search. So we have our root. And then if not root, return -1. Left is equal to depth first search left. Right is equal to depth first search right. Res is equal to maximum of 2 plus that. Return 1 plus max. So this is the actual diameter, I think, but this is the, oh wait, no, this is the diameter and this is the height, I think. So yeah, if not root, return -1. Then we basically say the left is equal to self.dfs root.left, right is equal to self.dfs root.right, and we basically want to return 1 plus the maximum of root.right and root.left, and we're saying that res is equal to maximum of the res, maximum of that left and right, I think. So was it? No, left plus right plus 2 plus 2, I think so anyway. Yeah, I find it interesting why he used a list of 0 instead of just using 0, but you know, what do I know? Yeah, and we don't need self here because it's not part of the class function. So just run that. See how that works? Okay. Local variable res reference before assignment. Okay. Was that why he did a list of 0 instead of just defining 0? It could be. Yeah, this is quite interesting. Like, I still don't really understand how this algorithm works realistically. So let's just kind of like walk through it. So first we define, let's just try see if this works without it being a list. I feel like it wouldn't, but we'll see. Return res. I don't think this will work. Yeah, that's interesting. Okay, I guess that makes sense because DFS is like it doesn't have access to res, maybe, I don't know. So let's see. Okay, so res is a list of 0. So then we define this function root. If it's not root, return -1. So then we do this for left and right. So basically we're getting the maximum diameter. Wait, are we? No. Yeah. This returns the height, not the diameter. And then, but because we have the height, we basically want to say that the res is gonna be the maximum of that, and the left and right +2. So I guess that kind of makes sense. It's just kind of a bit more confusing because like a lot of things is happening with each recursive call. Because number 1, you're computing the height of the node, and then number 2, you're also computing the maximum width or diameter rather. So yeah, that's quite interesting. I think I definitely need to revisit this, so I'll just start it for now. But yeah, I think that's it for today, mainly because I want to make sure that next time we can do 3 more questions before we move on to tries, or actually it would be heap. Yeah, so that's fine. I think I'll probably end it there, just on a little sour note because we didn't really get to implement this ourselves, but that's fine. It's all part of the process. I think for next week I'll probably come back to this and see what happens. Like I'll try to not memorize the solution, but see if I can come back to it and see if I understand it. But yeah. Yeah, I did do this like a bunch of times, but like it's all basically just the same thing, and I don't really understand it even right now. I'm a little bit shaky on it, but that's fine. So yeah, I think that's it for this stream. I'll probably, yeah, I'm definitely gonna stream again next week, and hopefully upload a video next week as well, maybe. I'm not sure. I think I want to definitely work on more interesting projects, like not necessarily more interesting, just something that will take a bit more time, just so that I don't have to constantly think of new projects, because then that would be kind of weird. I think my next project will be working on my personal portfolio website, and we're gonna expand that to make it as technically complicated as it could be. So yeah, I'm excited to start that project, and I'll still keep doing these kind of leak code streams every Sunday. Maybe I might start doing it on Twitch instead, but we'll see, because I'm not sure. And yeah, thanks for watching, and I'll see you, I guess, next time maybe, I don't know.